Hello, everybody. Thank you for joining us today. You are part of the 200 people worldwide who have registered to this webcast. It is powered by Yole Development and Solmates, and it is dedicated to pulsed laser deposition. My name is David Jordan. I am Global Sales Support and Coordinator for Yole Development. So before we get started with this webcast, I would like to give you some practical information. First, you have the possibility during all the webcasts to submit questions. In order to do so, you simply have to use the box at the bottom of the screen labeled Ask a Question. We will answer as many questions today as time allows us. And for the remaining questions, we will follow up via email. Concerning the materials and contents, please note the presentations are available and downloadable in the resource section of the platform. Furthermore, you will receive an email after the webcast with the link to the recorded session. So today, we are pleased to welcome Cédric Malaquin, Technology and Markets Analyst, RF Devices and Technology within Yole Development. Also, Arjen Janssen, CEO of Solmates, Bart Berenbach, Chief Business Development of Solmates, and finally, Laura Soos, PhD student from CELAD. So let's start the webcast with an introduction held by Cédric Malaquin. The data presented by Cédric are extracted from our latest report, 5G's Impact on RF Front End and Connectivity for Cell Phone Report. Cédric, it's your turn.
Hello, everyone. Thank you, David, for introduction. First of all, I'm glad to be here with you today for this webcast on pulsed laser deposition technologies from Solmates. I will give an overview of the 5G market and will orient it toward the filter market technologies. I will start this talk just introducing the 5G commercial availability. The network has been launched in Asia. It also has been launched in North America and in some countries in Europe. There is also some turn of the 5G network across Middle East and also Africa, also Australia. And in terms of mobile subscriber, we can see there is a big advance of the subscriber around the Asia. However, all the world is trying to catch up and to increase the number of subscribers. In terms of number of smartphones, the result is the 5G technologies penetrates very fast into the mobile handset market. Looking at the smartphone market from 2020, it is expected to reach at least 200 million units of 5G device by end this year. And it will likely continue growing and penetrating the smartphone market. 5G, in terms of technology implementation, is quite different compared to previous generations, meaning LTE, 3G, and also 2G in a way. There is many features that are included in 5G smartphones that were not included in 4G handsets. Features such as MIMO, downlink, 4x4 is mandatory features for handset. For frequency band above 2.5 GHz, which has a huge impact of the number of RF chain integrated in a handset and thus the number of filters. It's the same for the uplink. In some cases, there is some technology such as the MIMO uplink 2x2 MIMO, which is also a requirement to be integrated for certain band. So again, more filters that have to be featured in the phones. And also there is other type of features such as a diversity transmit. There is dual connectivity, meaning you still have a LTE connectivity on top of a 5G connectivity. So no decrease of the number of filters at all. And in addition to that, there is other features such as the higher power UE requirement that have some impact on the design of filters and other components. Another point which is really important is the wide bandwidth that is brought to the market with 5G new bands such as V band, N41 and so on. It leads to new type of designs to be integrated in the mobile handset so that the technology can be live. How does it translate to a handset architecture? So if we take basically an entry-level phone, which is an LTE phone, it's some components integrated in the phone from 20 to 30 filter die are used in this typical mobile handset. If we go to mid-tier LTE handset, it's close to 30 and 50 filters. And if we go to high-end 5G luxury device, it's more than 50, up to 80 filter dies that are required in a handset. So it's a huge amount of material. And with that, there is a problem of cost performance equation, as there is more and more filter to pack in a handset, but there is less space to pack the filters. A lot of innovation is required to improve the form factor of the filters. Also, the cost of the filters is important. So it leads to innovation in packaging. There is also a big pressure for yield improvement. And there is a trend toward multiple filter aggregation in a single die. Also carrier aggregation pressure that leads to more quadplexer, hexaplexers, and so on, so n-plexers. More complex filters are coming over time. To build these filters, there is a variety of technologies that can address the multiple bands of frequency to be addressed, and also the multiple bandwidth requirements. To just name the different technologies, we are talking there acoustic wave technologies. There is the well-known legacy technology, which is SAW, surface acoustic wave technology. On top of that, there is the temperature compensated SAW, which is kind of an improved technology enabling a good behavior when the temperature of the device is changing. There is also a new type of technologies that are emerging, which we call thin film surface acoustic waves. Basic idea is the film of the piezo layer is thin compared to the SAW technology. It's not a bulk acoustic wave. Then after, there is the bulk acoustic wave technology. There is multiple features of it. One is the BOSMR, solid mounted resonator, and the F-bar technology, which is the membrane built on top of a silicon substrate. And to complement the filter technology portfolio, there is also multi-layer ceramics and IPD type of filters that can address several bands. Looking at the technology landscape, each technology has players that have developed their own IP and products. And if we go to the high-performance filters, such as the temperature compensated SAW or thin film SAW, also the BOSMR and F-bar filters, there is not a big list of players that can play into those type of high-end filters. And it's interesting to see that all of these bricks have been developed by these players to have a complete portfolio of technology and address the multiple needs of the market. Looking at the market size, what does it mean in terms of number of components? So we estimated in 2019, the number of filters were 56 billion units of devices, or number of die. and we expect it to grow more than 4% up to 76 billion units by 2025. Looking at the different technology portfolio and how it is evolving inside, what we see is the high performance filter technology that take more share into the market. So compressing the BOSMR technologies, also the F-bar technology are gaining more traction on the market. And there is also the high-performance TCSO and TFSO filters that are raising some interest by the industry. So looking at the wafer needed to support these different technologies, we have a multiple type of wafers to support it. So first type of wafers are the lithium tantalite wafers. We converted it to 6-inch equivalent, showing the growth from 2019 to 2025. It's roughly 3% growth of this type of substrate, mainly to support the SAW filters and also the thin-film SAW technologies that penetrate the market. Looking at the other type of substrate that are used for filter technology, you have the lithium niobate, and again, it is given in a 6-inch equivalent. We see in this typical type of substrate, the growth is much more higher, 10%, as the effect of the technology penetration, the TCSO, which is more and more used to build some complex filters that are embedded in modules, RF modules for the onset. There is also interest on this type of substrate for the thin film SAW technology, as the properties of the lithium niobate are really interesting to get good performance, high Q factor, high coupling coefficient. And then after, there is the silicon substrate that are used to build both technologies, so both F-bar and SMR. Again, the growth rate of this type of substrate is really high, plus 11%, as there is more and more product and needs for advanced filter technologies. There is also some sapphire wafer that are used by some players, but I'm not showing any growth rate there, as this is not really a trend to move forward. It's just a special type of approach from several players. So with that, I will let you the floor.
Thank you very much, Cedric, for your nice presentation. So once again, let me remind you that you can ask questions for the Q&A session and use the Q&A button on the platform. So now we will continue the presentation with Arjen Janssen and Bart Berenbach from Solmates. We will also have the pleasure to welcome Laura Soos from CLAT, who will also make a brief contribution to the webcast. The floor is yours.
All right. Good morning, good afternoon, or good evening, everybody. Thanks for joining this exciting event. This is Arjen Janssen, and I'd like to thank the whole team for hosting this. And Cedric, thanks for showing us in these slides why we are here today. It's clearly seen that the 5G train is accelerating fast, and the demand for higher full frequencies and lower costs is a great opportunity for new technology like us to jump in. But before we get into that, I'd like to say a few words on Solmates. Solmates exists already since 2006, and we have a razor-sharp focus on bringing PLD to the production market. That's the only thing we do. And I cannot emphasize this enough, but this is due to our great employees. They have a great drive and are very skilled. I'm very proud of this modern company. And the management here on the screen, you can see Martijn Dekkers, Christian Beum, Wieke Hopman, and Bart Berenbach, who's also here in the call. are very proud to lead this company with their experience and with their unbelievable perseverance. And I have to be honest, we pivoted several times for our position in the production market, and now we found it. And for me, I founded this company together with Martijn Dekkers, and it's just a pleasure to be a CEO of this team and to serve the company towards this production industry. Before we continue, I also like to show that we have a very experienced board members with great experience in the semiconductor industry. I'm very happy to have them on board. And of course, we're backed with our solid investors who also are in there for our mission. Leaves me our agents, our representatives, and also the academic network that we have built up in the last decade. And before we move to Bart, because Bart is going to tell you all about what and how about PLD, I just want to emphasize why we are here. And I speak for the whole company. The reason why we're here and why we are working on this technology is because this technology is different. Our customers are telling us that this is a different technology. And a different technology always brings new opportunities for different processes that allow for different applications. Of course, every new technology also has its challenges, but these differences, and we'll get back to that later on, is the main driving force of this company and where we stand today. I think it's also a good indication why a company as us have grown even in these uncertain COVID times. So, Bart, up to you.
So, Arjen, and this is also the reason why I'm excited. So I joined a little over a year ago because of the Solmates mission. Solmates is going to bring this technology to volume manufacturing. And that's an exciting phase. I've spent some time in volume manufacturing. I know what it takes. I've had my all-nighters fighting tool issues, solving particle problems. And Solmates is making the bold move, bringing PLD to volume manufacturing. So this next half hour, we'll be talking roughly 4 topics. So at first, we will show you a bit about our new PLD platform. So it was announced last year during the Semicon. So it's a year ago. We assembled it in 2020. The whole engineering, parts procurement, assembly during COVID times wasn't easy, but it's here. And we'll get it manufacturing ready next year. We'll speak a bit more about that. Then the basics of PLD. We have a very neat little animation movie that will help. And then this webinar, we dedicated it to the RF landscape, so BAW filters and SAW filters. So we will give you 2 showcases. So one showcase I will present, it's about highly doped scandium aluminum nitride, and the other one Laura will present. So it's it's early work on our collaboration about lithium niobate for SAW filters. And I think Cedric, in the one before last slide, if you look at the gaggers, so the growth of these markets, it's both BAW, SMR, and thin film SAW. So we hope that these materials raise interest for people in that field of manufacturing. All right. So before we go to the animation, Arjen, can you explain a bit?
Yeah, as I said, thanks, Bart. As I said, we already started in 2006, and I think this picture shows that of Martijn Dekkers, one of the founders in his early days. And if you look closely to the machines that we have developed and are in the market, then you see that almost every 2 years we were able to produce an improved platform, not only improving the uniformity, but also the particle levels with improved droplet trap filters, which will be discussed later on. And I have to be honest, I think today, when we already have shipped and installed a few of the last systems here on the slide, it brings everything together. This is the tool that we have developed in order to adapt to the customer needs. It's a tool that is cluster compatible. It brings all the knowledge we have into this beautiful piece of equipment. And that's why we are here today to say more about it.
All right. So, Arjen, you stole my thunder. So here it is, cluster compatible, wafer facing up to 300 millimeters. So this is a picture which has a single wafer load lock, but this same system, equally simple mounts to all mature handlers. So I'm very eager. I like hardware. I can talk about hardware for another hour. So if you want to know more about the design concepts of this system, please contact us, and we can talk you through all the neat features of this equipment. But what we really want to show you is a bit of an introduction into PLD, into the basics. And quite often we use our hands and we make gestures on trying to envision how it works. So what we did is we made a video clip to show it. So what you see in this video is our I hope it runs. Yes, so it's here it goes. So it's a pulse laser. It's a very powerful pulse laser. You can see that the target that we're using, so the source material, is relatively small compared to the wafer. So here's this little zoom in. So it's a square target. We are ablating material and we are creating this plasma plume. There is no argon, not an argon plasma. We don't need to keep it current going. So all the energy of the plasma plume, all the energy comes from the laser, right? So there is some background gas to control pressure, but the laser is what makes the plasma. It takes a couple of pulses only to make a monolayer. It's a local monolayer on the wafer. We need to fill the entire wafer, of course. But this plasma has excited species, and by scanning the wafer versus the target, you can see that we can build up an entire layer. So this was a less than 1 minute introduction into the PLD basics. There's much more to it. Maybe, Arjen, can you summarize for us?
No, I think in the beginning I said why we are on this mission is because we believe and see that this technology is different. And if you look at the pictures, the stills from the video, but also to the physics behind it, you can see that the main difference with sputtering, which is where we are compared to the most, is the density of species in the plasma. That's more than 5 orders higher than in sputtering. And of course, the plasma is very local. It's a bit of the size of an apple, but the density is very, very large. In combination with the high excitation energy of these species, this results in a very dense cloud of a supersaturated plasma. And this supersaturation allows for easy nucleation and easy formation of materials, even very complex materials. And not only that, if you look at the technology, it also allows to transfer we call it complex, or actually stoichiometric complex materials, one-on-one from the target to the substrate. And I think a very interesting part of this is this local nature that allows us to give also local control on the thin film properties of the wafer across the wafer. And I think this is a unique part in the semiconductor market.
All right. So also seen here, it's the target material is important. We'll talk to that. Throughput is important if we want to do high volume manufacturing. So we're doing pretty decent PVD. Like it's good throughput. It requires high powerful lasers, so we use coherent lasers. And again, the local deposition. We will talk to that topic in a bit, and then in the context of stress control, which is hugely important for scandium doped aluminium nitride. But first, there's another topic we need to talk about, and it's an important topic. I already mentioned a bit of it, and it's particles. How about particles? Many people that know about PLD say it's great. You can make fantastic material systems with PLD. But how about the particles? Well, Solmates technology, a lot of the technology is about particles, making sure that the particles are filtered out. You could already see it in the slide that Arjen presented. We're now on the 3rd generation of our particle filtration technology. And the other part of it is, of course, make sure particles aren't formed. So it's a combination of both. Having control over the ablation process, making sure that we minimize the amount of particles being formed. But the other part is key technology. It's the key of what sets Solmates apart from others, the ability to filter particles. There's a very small graph in the top. It's our roadmap. It's a very aggressive roadmap that's been drafted a couple of years ago. We've been able to keep track, so we are on schedule with that aggressive roadmap with more to come. I'm sure people want to learn more about this. Contact us and we'll tell you more about our particle control technology. And we'll also talk about it a bit in the context of the deposition target itself. But let's move to the showcases. So we will do one showcase, scandium doped aluminium nitride, for both filters, and then in a couple of slides from now, we will have Laura present the update on lithium niobate. So if we talk about scandium doped aluminium nitride, we chose this webinar to focus on the RF application, but this material is much in need for other applications as well, for the sensor people, PMUTs, microphones, speakers, and many more. But if we talk to filter customers, this is what they say in terms of manufacturing needs. So it's coupling factor, right? Scandium doping increases your coupling factor. You never have high enough coupling factor. And of course, coupling factor is also very much device dependent. So if we do our 30% scandium optimization, that's the core of our focus, then we can, from the material properties, derive the theoretical value of a coupling factor of 17. So clearly, it's up in it's in the upper range of performance. Coupling factor is important, but the other thing that's really important is uniformity in coupling factor. This is well known. Stress in the layer and coupling factor are related. So therefore, what we need to do as an equipment supplier, make sure that we have uniformity in stress. There is never enough uniformity in stress. This is directly linked to yield. The other thing, we like to claim that we have an upside in terms of the quality we offer, but there is a big price pressure. There's a fundamentally big price pressure. There's more filters per cell phone, and in the bill of material for advanced cell phones, the whole RF front end is a big part. So manufacturers have a big cost reduction, and what we do is we have a very reliable supply of targets where we can make these high scandium doping, which is very much non-trivial in the PVD landscape. So in the future technology, so with the higher frequency bands in the sub-7 range, the resonance frequencies, they go up. So the layers become thinner. And as the layers become thinner, you need really good quality material, but you also, in terms of optimizing the coupling factor, you need even higher scandium doping. So we will show you one slide, the proof in the pudding. We did also some work on 40%. It works well, so hang in there. So first the basics. This is for 30% scandium doped aluminium. We want to show you some basic performance numbers. So there's a good E31F. The tunable stress range, we can go from compressive to tensile over large range. Stress uniformity, 50 megapascals. And this is an important number because this is full range, right? So this is maximum minus minimum. Some people report half range, but we report full range. Thickness uniformity, everybody knows it needs to be uniform because the thickness is the resonance frequency, and otherwise you head into cumbersome trimming. Rocking curves are good. Surface roughness, it's pretty smooth, as you can also see from the cross-section. Crystal pyramids, also called abnormal outgrowth, very important factor. We can do that. We can control the stress also for 40% and have means and ways to minimize the crystal outgrowth. So we claim pyramid-free deposition. Particle impact on yield, yes, there are particles, but from the demos, from the work that we did, we get positive feedback, very little impact on yield. And of course, this is an easy claim to make from our side, but if you want to assess this for your manufacturing needs, then that's a topic that needs attention. That's a topic, of course, that you want to determine for yourself. But we felt a lot of encouragement from these results. So, like I said, theoretical value, we can do a coupling factor of 17. We know more about it, but cannot share. The bottom one, so the dielectric loss tangent, it's typically not a parameter high on the list for the RF people, but it's been measured by several parties, and it seems that the dielectric loss, even for 30% scandium, because the losses tend to go up with scandium doping, it's really low. It's fundamentally lower compared to references from the PVD world. And it indicates our earlier claim. It's fundamentally good material. Also, the initial growth from the electrode, it grows relatively well right away. No complex seed layers necessary. It's a good material. So stress control, we already mentioned it. In RF filter manufacturing and BAW filter manufacturing, stress control is very important. So we have a local deposition. That's what we showed in the animation. And it means that we can also locally make variations. We can locally control the deposition. We can locally control the stress. So either we go for best-in-class uniformity, and that means that we can go to 50 megapascals. We think we can do even better. At the moment, we're hitting the limits of the metrology tool. So the metrology is limiting progress here. But we think we can do way better than 50 megapascals. But even one step further, sometimes in device integration it's desirable to intentionally induce a non-uniformity. If that helps with a filter stack, with a device stack, if multiple layers stack to each other, we need to compensate for non-uniformities in another layer, then we'll take up that challenge. And the two graphs here, they're pretty extreme. It's a large variation in stress, but it's flexing our muscles a bit. But if we need to flip the profile around, then I hope these graphs illustrate that we can do that. Reiterating, it's seizing the advantage of the local nature of pulsed laser deposition. All right. So quick slide. The piezo performance is maintained, so even over a wide range. So let's talk about targets, because scandium-doped aluminium and targets, that's the topic. I think the people that do scandium-doped aluminium with PVD, they know that highly doped scandium targets, especially low oxygen, well, that can be a problem. They're very expensive, and it can even be problematic to get your hands on it. Well, Solmates has the solution. So we've developed our own ceramic target. And the word ceramic here is important. It's not an alloy, right? What we do is we have a scandium-doped aluminium nitride. The nitride's in there. It's a ceramic target, and we do a stoichiometric transfer. So the source material, we transfer it to the wafer. It's the same. And therefore, it's fundamentally different. And it's low cost. It's small size. The same size can do 200 and 300 millimeter at high productivity. And there is no problem to get to 40%. Well, and why not a little above, right? Thinner layers, like I said, for higher frequencies are also important. The graph in the bottom right illustrates another issue that we don't have, and that's scandium gradients over the wafer. Like I said, it's stoichiometric transfer. So the scandium concentration is the same all over the wafer. So that's nothing to worry about either. Proof in the pudding. We focused our core research on, our core research on 30% scandium. But we also just put in a 40% target. I mean, we've said to people, there's no reason why we couldn't do 40. So we decided to put it in there, and it works really well. It's just a couple of weeks' work. So what we can do with 40% is very stress, same way we did it for 30%. But the people that work with us will know that it becomes increasingly difficult to suppress, to avoid pyramids. So we managed to do it in a couple of weeks. We grow 40% scandium layer, pyramid-free. We can even do tensile. The within wave uniformity, the best run was even below 40 megapascals. So we think we're doing pretty good there. XRD looks good, and there's a high potential for further optimization. So this is what we we want to show you as the promise for the future. All right. Summing it up, we're saying we have a manufacturing ready solution. In a way, our proposition is easy, right? Our proposition is superior quality at a fraction of the cost. And this is what we demonstrate. So we're currently in the phase to prove this exciting technology in a manufacturing environment with launching customers. And of course, we understand that we can show really great performance features. But we also understand that integration of new technology it's a lot of hard work. So it requires a lot of device integration. And of course, it requires a lot of effort to reach the desired product reliability. So our vision is that we do that together with customers, and we know what we're up to. So besides aluminum nitride for BAW filters, we have another exciting PLD application for SAW filters. So welcome again, Laura. So thanks for joining. Can you update all of us on your latest findings?
Yes, thank you very much, Bart, and good evening, everybody. Thank you for your invitation. As you said, I'm going to present our work on the epitaxial growth of lithium niobate by PLD. Just a small precision, as Arjen presented all the optimizations the Solmates team has already on the common issues induced by PLD. I'm going to talk about has not been realized with the latest of their equipment, and yet it is very interesting. The context in which the latest collaboration takes place is the upcoming 5G and the technical enhancements it requires, such as a high performance RF filters. They are made by several acoustic devices, which are either SAW or BAW resonators, and each their pros and cons. The surface acoustic wave resonators are combined with monocrystalline wafers of lithium niobate or lithium tantalate, for instance. They are low cost, but also limited, for example, by the etching. The bulk acoustic wave resonators are made on with piezoelectric layers such as aluminum nitride. Address high frequencies but are expensive as they require several conditions. The deposition of lithium niobate films a new path to, in the first time, process SAW devices with frequency for low cost, and then process both devices even higher frequency of resonance. The pulsed laser deposition technique is the perfect candidate for this, as the frequency applications require high crystalline layer of the stoichiometry, which is an important issue for pieces of lithium niobate. And finally, thickness control. Moreover, it could lead to the fabrication of low-cost resistors because it is cheaper than using monocrystalline substrates, and also it can be included in an industrial flow. This is why we have decided to collaborate with Solmates on the subject and try to perform a homoepitaxy of lithium niobate. This time we used lithium niobate substrates of different crystals and deposited a 200 nanometer layer thick lithium niobate. We wanted to test in the first time the quality of the process before further experiments. And the results are promising. The crystalline quality of the layer are excellent. Diffraction analysis performed indicate that we have narrow rocking curves for all the layers, but regardless of the crystal cut, we have low value of full width data maximum. Thus, the crystalline structure of the layer is similar to the substrate and for all the samples. We tested the X cut, a Y cut, and moreover, transmitted electrons microscopy analysis points out that we have a defect-free between the substrate and the layer, as illustrated here with a Z-cut sample. Our concerns are a bit more about the roughness and the droplets that could have resulted by the deposition. However, as the AFM images show, we had a low rate of droplets and roughness values close other classic PVD techniques. And finally, Raman spectroscopy analysis, a comparison between bulk substrate and the substrate plus the layer by PLD. These analyses confirm all the previous results, such as the samples have a low roughness, low defects, and a stoichiometry close to it. From our point of view, PLD seems to have a bright future for radiofrequency device applications. For solar technology, it will help reduce the production by enabling a process on silicon substrates, but also reduce the production time and even maybe be developed for large substrate sizes. Moreover, external underlayers could be used under the piezoelectric sensor. And finally, the thickness of the piezo layer can be controlled. Is also an interesting feature for both technology. Both technology could also be very interested in pulsed laser deposition techniques. It could act high frequency as well as reducing the cost of production, for instance, by making the entire stack of the bottom electrode, the piezo, and the top electrode inside the same equipment. As for Leti and Solmates collaboration, on one hand, the deposition process of lithium niobate thin film will be transferred, and we will try to optimize it to be able to demonstrate the process on various and large substrates. And on the other hand, the Leti will use competencies on silicon fabrication to demonstrate the high frequencies that can be reached with radio frequency filters in lithium niobate thin film grown by PLD. All this will be with the installation of the first 200 millimeter bridge tool of Solmates that will operate at the beginning of 2021 at Leti. Thank you for your attention.
All right, Laura, thank you. Thank you. So this was a very nice talk, Laura, and it hopes to illustrate the potential of PLD in the 5G connectivity landscape. So we're heading towards the end of this webinar, and the title of this webinar was Finally a Manufacturing-Ready Solution. So summing it up, this is our vision, and we build it. We're also showing some software screens to illustrate the point of the importance of automation. Solmates decided a decade ago to work with a software platform from the peer group. We're working with PTO7, throughput 3 to 7 wafers per hour. And there's a very strong continued focus, of course, on particle reduction. Even in this difficult year with COVID-19, we are expanding the company, Team Solmates. We're expanding the facilities, the R&D lab, the assembly capacity, and we're expanding our network of sales representation in Asia and North America. So, Arjen.
Yes, I think we're almost at the end of this webinar, and we hope we were able to show you what the potential is, and also what Solmates PLD can offer to you. I'm pretty sure by now that you also see why we are so enthusiastic about what we're doing. As said in the beginning, the Solmates PLD train is on the move, and we just invite you to jump on board and work with us towards integrating this technology into your chipsets, into your fab. I mean, we understand and we recognize that delivering quality is very hard. It's hard work for all parties, and that's why we believe in teamwork. David, back to you.
Thank you very much for all this relevant and interesting analysis. We are now going to wrap up and finally get the Q&A session. So we'll answer as many questions as time allows us today. And we'll begin with a few questions for Solmates. So the first question is, what control do you have over substrate temperature during deposition? And what temperature can customer select?
So it's a good question, because for scandium-doped aluminium and epitaxial growth, that's different temperature ranges. So we use a heated chuck, and the aim is to go up to 750, maybe 800 degrees, and that's more than enough, at least for scandium-doped aluminium.
So it's a wide range of temperatures that can be selected. And as Bart says, it's on the high side for also other materials that you want to do, but also lower temperatures are of course also possible.
All right, thank you. Another question: which metrology equipment are you using for stress metrology?
Yes, thanks. I think stress measurements are very important, and we use two methods. So we use a capacitive way and also an optical way. The capacitive way we use an EH metrology, and the optical method we use the Flexus tool.
All right, thank you very much. Last question for you: what wattage of laser do you currently use in the most powerful systems?
So that's a good question. This also touches, of course, what the throughput of a system can do. Currently, we are mainly using 100 watt lasers, and we are now in our lab setting up 300 hertz lasers to match the PVD deposition speeds.
Thank you very much. Now we got some questions for Cedric. Cedric, what are the wafer size used for the wafers?
Such a marked.
Cedric, are you there?
Yes, sorry, my mic was on mute. Yes, it's a good question. Indeed, the manufacturers are working with a small size of wafers. So for bow type of wafers and FBAR type of wafers, it's mostly 8-inch. It remains also some 6-inch volumes. And for the SAW type of wafers and lithium niobate, lithium tantalite is mainly 6-inch.
All right, thank you. Our last question before we end this webcast: will 5G bands above 3 gigahertz be addressed by acoustic wave technologies? Cedric, did you hear me?
Yes, can you please repeat the question?
Yes. Will 5G bands above 3 gigahertz be addressed by acoustic wave technologies?
Yes. Yes, the answer is yes. There is now technologies that are used through APD type of technologies and MLCs, but there is interest in going to acoustic wave type of filters to get better performance with precision of the band to be filtered. So there is some development ongoing to enable this type of filters to reach the right performance.
Right, thank you very much. So the webcast is ending. A big thank you to all our speakers. By the way, let me remind you that you will receive tomorrow an email with the link to the recorded session of this webcast. And also feel free to share this presentation and our analysis to all the persons that could benefit from it. And do not hesitate to contact us if you have additional questions. You can find all our contact details on the last slide of the presentation. Also, please be aware that your analyses are extracted from our market and technology reports, and you can find them on our website, i-micronews.com. Thank you very much for joining us today. Have a good day. Stay safe. Goodbye.
Right.